This is the first of two videos in which we're going to look at redox in biochemistry. Turns out understanding redox is really important for understanding metabolism, so it's worth doing some work to lay groundwork before getting into specific metabolic pathways. So I said in an earlier video that what cells are doing in general is they're betting on environmental redox gradients. And I likened this to stock market traders who are betting on the long-term growth of markets to make money over time. And cells do the same sort of thing. They're betting that there's going to be some kind of redox gradient. There's going to be reactants around that they can turn into products, and that's going to be a favorable process that they can exploit to grow and thrive and do all the things that cells do. If that isn't interesting and motivating enough for you, you can consider these two athletes, Beatrice Chebet and Faith Kipyegon, who, as the day before, so yesterday, when I'm recording this, both broke world records, one in the 5K, one in the 1500 meter, and they did these incredible athletic feats entirely powered by a single redox reaction. Basically, these two women have specialized in very rapidly and efficiently converting glucose and oxygen into carbon dioxide and water, which means if we're going to understand how humans perform, how we do all the amazing things that we do, we fundamentally need to understand how redox chemistry works. And so, I'm putting this whole sentence here, right? To understand biochemistry, we just have to understand redox. So what I'm going to do is I'm going to go through this in 4 stages. What is a redox reaction? Quick review of that. What are some of the biologies of redox reactions? So looking at some biological redox reactions and how they're used. We're going to ask how we can identify redox reactions. And then actually, I broke it out into its own video because it was getting a little unwieldy. We're going to actually go through how do we calculate the energy of a redox reaction. So let's just start launching through these. So a redox reaction is a reduction-oxidation reaction, abbreviated redox. And what these involve is a transfer of electrons from a donor to an acceptor. So here I'm just drawing this generically as X. Come on, pen. We're going to zoom, not laser. There we go. X has these 2 little dots on it. Those 2 little dots go from being on X to being on Y. So we're doing a redox reaction. We're moving electrons from one molecule to another. Because of this process of moving electrons around, redox reactions are always going to come in pairs. So we're always going to see a donor and an acceptor. In terms of language, we would say that during this reaction, the donor X is being oxidized while the acceptor is being reduced. So we're seeing electrons go from X to Y. Oxidized just means loss of electrons. Reduced just means gains of electrons. That's the language that's used. So if it's not obvious to you, that's just a fact you have to learn about the universe. So we're going to oxidize and lose our electrons. We're going to reduce and gain electrons. Now, how does this end up playing out inside of a biochemical context? We're moving electrons around. What matter? Well, to help set this up, we need to add one more other piece of information, and that is that atoms differ in their electronegativity. And what that is that's the power of an atom in a molecule to attract electron density. This is the Pauling scale that I'm showing here. But basically what this scale is showing is that oxygen has a high affinity for electrons. Phosphorus has a low affinity. And what I've done here is I've organized the CHNOPS atoms, our 6 most common atoms in cells, in terms of their electronegativity. So we see there's this gradient going from oxygen up to phosphorus. So again, oxygen has a high affinity, phosphorus has a low affinity, and the rest of the atoms fall somewhere in between. What that means is if we can transfer electrons around between atoms with different electronegativity, we can maybe gain some energy from it. And so actually, it turns out that the most important thing is the placing electrons between, I should look at what I've written up here. Favorable redox reactions place electrons between atoms with different electronegativity. Electronegativity. And to illustrate this, what I've done here is I have taken each of the CHNOPS atoms, and now I'm imagining a bond between them, and I just plotted down here the difference in their electronegativity. So this is kind of an empirical scale. This isn't something you would use for a calculation, but hopefully it helps us set our intuition for how these systems are going to behave. So we see on the left, we got a block that's pretty similar. We have a middle block, and even more to the far right block, and then finally this block over here that's all the way on the side. And let's start on this side. What we see here is an oxygen bound to, say, a hydrogen. So it's a very large difference in electronegativity right there. And then over here on this far left side, we have atoms that have the same electronegativity balance. So there's still oxygen involved over here. There's still hydrogen involved over here. But these two atoms, the electrons are shared between atoms with the same electronegativity. What we can think about is if an atom is shared, say, between two oxygen molecules, it can't really interact favorably with either oxygen molecule, right? It's stuck. It can hang out with one a little bit and the other a little bit, but say these electrons can't spend the time that they want to with, say, an oxygen. Whereas if we go over here to this scenario, well, we're going back. If we go over to this scenario where the oxygen is bound to the hydrogen, the electrons can spend all the time they want with the oxygen. They get to spend more time with a more electronegative atom. That is a favorable position to be in. It's so favorable that if we look at what I would think of as sort of the purest sort of redox reaction that we can think of in this context, you can get a ton of energy out. So this is this is a hydrogen gas here with a molecular oxygen. When you react those together, you get water out. And what that means is we're basically taking electrons from hanging out between hydrogens and between oxygens, and we're moving them all the way to the far side of this. Huge difference in the electronegativity between the atoms now. It's extremely exothermic, and it's so exothermic that it's actually the reaction that's used to power the main stage of the NASA's SLS rocket. Right? Extraordinarily energetically favorable, all because we're moving electrons from hanging out between atoms with the same electronegativity to being between atoms with different electronegativity. Okay, so that's the logic of redox reactions and how cells are going to use them. Now what I'd like to do is dig into a collection of different biological redox reactions to understand what's happening there. So here is a set of 5 different redox reactions that are, there we go. There are 5 different redox reactions that are done by different organisms. So we've got on the top, this is the reaction that's done by a class of organisms known as methanogens. This is the anamox reaction. There are others here. We're down at the bottom. This is human. But the idea is each of the creatures that runs this reaction is using it to extract energy to do interesting things. And what I'd like to do is look at 3 of these reactions in the sort of way we just looked at the hydrogen-oxygen reaction. So back on this energy scale here. I'm just going to make myself go away. So the first, this is something that's done by methanogens. What methanogens do is they take in hydrogen gas and carbon dioxide. And what I'm going to do is just count the number of electron pairs that are between different atoms. So if we look here, we've got H, H. That's an electron pair between the hydrogens. There's another one. This happens 4 times. So we have, because there are 4 hydrogen molecules. So basically we have 4 electrons that are hanging out between hydrogens. And then if we look at our carbon dioxide, we have 4 electrons that are hanging out between carbons and oxygens. And for simplicity here, just to illustrate this concept, I'm not worrying about the difference between double bonds and single bonds. That will matter quantitatively, but it's not going to matter qualitatively for understanding where the energy for these reactions comes from. So we have 4 bonds here that are lurking between oxygens and carbons. All right, so methanogen comes in, it grabs onto some hydrogen gas, it grabs onto some some carbon dioxide, it does a reaction. What it spits out is methane. That's why they're called methanogens, because they generate methane, and water. What we can do is count the electron positions here. So we've got H, 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 H. There's our methane, so we've got 4 CH bonds, and then we have 2 waters, which, water, right? So we've got oxygen, hydrogen bonds. We have 4 there. And now what we can do is plot this on our graph. So we started out with 4 of these, and we started out with 4 of these. We ended up with 4 of these and 4 of these. So overall, net, what we're doing is we're taking electrons from being shared between atoms with the same electronegativity to being shared between atoms with more different electronegativity. That releases energy. That energy difference can be used to power cells. Okay, let's look at another one. This is methanogens, or not methanogens. These are anamox bacteria. Anamox bacteria take in ammonia and nitrite. And if you go through the exercise that I did, like with hydrogen gas, and like what you get is that they have an ON They have 3 of those, and they have 4 NHs, so those are here. What they then do is they turn that into molecular nitrogen and water. So they're actually going to go over here, make 3 nitrogens, but they're going to put these OHs over here. So those are 4 and 3. And so they're doing actually an interesting move where they're moving some of them, they're actually putting them between molecules that have the same electronegativity, between atoms with the same electronegativity. But they're also shifting 4 over this way. And just net, if you look at it, this is again very rough and ready, but there's 4 that are being shifted to being between more electronegative atoms and 3 that are being shifted to being between the same electronegativity. So overall, this reaction is still putting electrons between atoms with different electronegativity, and cells can use this to extract energy from the environment. Last thing I want to point out is just the reaction that we do, or that Chebet and Kipyegon do to go, set world records in distance running events. What they're doing is taking glucose and molecular oxygen, which if you do an accounting of all the bonds, looks something like this. And I don't want to go circle them all because it's going to get complicated looking. But at the end of the day, what we're spitting out is carbon dioxide and water. So basically all of our bonds end up in these 2 states rather than, we start over here and here and here, right? So we're seeing this massive shift towards placing all of the electrons, again, between atoms with different electronegativity. A lot of OHs in the waters, a lot of OCs in the carbon dioxides. Okay, so that's the sort of reaction that we're doing, but it turns out we don't actually just do this as a single reaction, right? So instead of doing all of that at once, which would give us the SLS rocket, or in this case, what this teacher is doing is she's blowing pure sugar over a flame that's burning in an oxygen environment, and you get this huge jet of flame, right? Instead of doing that, what we're actually going to do is we're going to break this reaction into a bunch of steps. And as we go through metabolism, what we're going to see is this is going to be the input, this is ultimately going to be the output, but it's going to take a million steps to get there. So even this is part of the reason the redox kind of hides in the system, is instead of seeing one giant redox reaction, we can say, oh, that's redox. But we actually see are a whole bunch of reactions, some of which are redox, some of which are not. But when cells do break things into redox reactions, what we're going to see a lot of are these molecules, NAD plus and NADP plus. They're going to be oxidized and reduced as part of this chemistry. And as we hit them, hopefully you'll start saying, oh yeah, there is a redox reaction. Another thing about redox in biochemical systems is that it actually correlates fairly strongly with catabolism and anabolism. It's not exactly perfect, but to a almost perfect first approximation. What you'll see is that catabolism involves oxidation of carbons. So carbons go from being up here to down here. So you're adding more oxygens, you're taking the carbons and you're attaching them to more electronegative atoms. So that's catabolism. Anabolism, by contrast, is a reductive process generally. So what we're seeing is you're basically taking the carbons and you're reducing them further. And it turns out that when we're doing redox chemistry in our cells, we actually use different redox molecules for these 2 processes. So mentioned in the currency video, but I'm just going to throw it out here again. We tend to use NAD plus to do oxidation reactions. So we take electrons, say from a carbon, and we stick them here onto NADH. So we tend to drive reactions we tend to oxidize carbons, for example, using NADH as the reducing agent. And well, that is not what we want to see. We're just going to wander over to another slide. And then we do NADPH for reduction. So we actually tend to keep around NADPH at high levels. And what that lets us do is then take electrons from NADPH, stick them on the carbons by moving electrons off of NADPH onto, say, a carbon. Okay, so what is redox reaction in a biochemical context? It's basically that we're going to be taking electrons, we're going to be transferring them between molecules, and that biology uses a transfer that involves taking electrons from being between more similar atoms to being more dissimilar electronegative atoms, and we can use that to extract energy. Last question I want to ask here is, when we're doing metabolism, when we're thinking about biochemistry, how do we identify, oh man, we have to worry about redox chemistry here? And so there are a couple of rules that you can just use. It's redox. A reaction is redox if it involves NAD plus or NADP plus, right? If these molecules are part of the reaction, that's a redox reaction, just by default. It has to be because that's what they're doing. They are doing oxidation or reduction. If you look at the reaction and you have the EC number for the enzyme, and the enzyme starts with a 1, that means it is an enzyme that's involved in oxidation or reduction. So that also means it's a redox reaction. Finally, you can look at the name of the enzyme. If the enzyme is named oxidase, reductase, or dehydrogenase, again, this must be a redox reaction of some sort. More explicitly, often what we're talking about are redox reactions using carbon. And so you can also look for changes in carbon oxidation number. So what that means is you can take a carbon and you can say, all right, for every bond that's bound to a less electronegative atom, like a hydrogen or a phosphorus, you're going to add a -1. For bonds to other carbons, you're going to add a 0. And for bonds to electronegative atoms like nitrogen, oxygen, or sulfur, you're going to add a +1. So for example, this is a biological reaction that happens. And what we're going to ask is what happened, and this happens inside of glycolysis. Sorry, I should have said that. So this is a real reaction that's happening during energy generation. What is the oxidation number of the carbon that I've highlighted there? And does it change over the course of the reaction? So it's actually a good chance to try it. So if you try to do that calculation, pause the video, grab a pen. Do we change the oxidation number of this carbon during this reaction? So maybe pause, maybe unpause. Okay, we're back. So what we can do is we can count the number of bonds to carbons, or to lesser, so we'll start here, less electronegative atoms. We've got -1 here. Bonds to carbon, we've got 0 here. All right, there's 1 carbon bond. And then we have bonds to electronegative atoms. We have 2 of those, so this is +2. So our total oxidation number of this carbon is +1, right? We just add those numbers up. If we look over here on the right, what do we see? Well, how many bonds to hydrogen or phosphorus? We've got 0 of those. We have still 1 bond to carbon, but now we have +3 bonds to oxygen. So now this carbon goes from a +1 oxidation state to a +3 oxidation state. That means this is in fact, a redox reaction. Okay, so hopefully that gives you some overview of what is a redox reaction, some of the biology of them, and how can we identify them. I'm actually going to do a second video now where I look at how to calculate the energy of a redox reaction. So hopefully you'll be able to join me for that. Thanks for your time, and I will see you later.